Hello everyone, my name is Tom Jose, Research and Development Engineer at Mirabilis Design. I welcome you all to the webinar conducted by Mirabilis Design on energy efficient AI workload partitioning on multi-core systems. So today we will be I'll be walking you through some of the problems and challenges faced while partitioning our software code onto the hardware systems and how efficiently we can do it, some of the analysis that can be done to tackle some of the challenges that we face. Those will be the main focus point of this webinar. So during this webinar session, if you have any doubts or queries, please feel free to type them up in the chat window and I will discuss them at the end of the session. While at the same time, if you're having trouble hearing my voice or having trouble viewing the contents on the screen, please feel free to interrupt me at any time during the session. So before we get started, a little bit information on the Mirabilis design. So the company was started in 2007 and is based in Santa Clara, California, USA. We have development and support centers in US, India, Germany, Czech Republic, Japan, and so on. And we are also the largest intellectual property and software provider for system level architecture exploration. This is because of the available. This is because of our library. Because our library components provides you with all the necessary components and the IPs required for you to model any system. So it can vary from an IP core designing or network system, software partitioning, software fine tuning, so on. And also we have the simulation tool, that is the Visual Sim Architect, has already been used for almost 250 components designing worldwide. So once again, the main product of the company, Visual Sim Architect, it's a modeling and simulation software. So what it is, it's a purely graphical environment where the user can drag and drop the components, make the wire connections, and then view the graphs, results, statistics graphically. So this makes the whole designing phase very much easier because the debugging is very much easier in this graphical environment. We can see the packets flowing through, the debugging is easier, then the statistics, all of them is very easier. So we use this graphical environment for performance analysis, software fine tuning. Then this also has third-party API integration supports. So before we get much detailed into the architecture exploration, I just want to take this time to walk you through what is the scope of the architecture exploration, system architecture exploration. So basically we start off with, this is done very much ahead at the earlier stages of the design implementation or design overview. So at the very first stages of design implementation, we are starting off with a certain set of requirements. It can be either from a research and development team or maybe from the customer requirements. We have certain goals that we want to achieve. So we start off with certain requirements. We can say that is available in a CSV file or maybe a piece of paper. Now, once we have the requirement, we start off with assembling a block diagram. The block diagram is simple representation of a flow of sequences. So once we have this block diagram ready, we will think about, okay, now what are the components that can be used to implement this block diagram? So once we have that, we will be looking into different parts of the design. That can be an IP selection, or it can be software performance tuning, or it can be the entire SOC specification itself. So, but it all starts off with the basic requirements. So once you have the requirements ready, next we will move on with the block diagram representation or the implementation, where we can use the Visual Sim Architect to explore different possibilities. So another important concept that we have to look for is how this process is taken care of. Like once we have the software code, or it can be an AI code or a simple normal code, how do we go along with it? So if we have the software code ready, then what we would do is we would take that code, compile it in the target architecture. It can be an ARM system or a RISC-V system, and we compile it, get the binary executables, and then we run it on the real board, or that for comparison purposes, or even we run it using the Gem5 simulator to get the executed trace from it. So once we get the executed trace, what we do is we will generate something like this. It's a CSV format file where we are going to input this trace into the Visual Sim environment. So once we feed that into the Visual Sim environment, we will run these traces line by line through the entire system. So we will be able to, once we run it through, the Visual Sim architect will generate the performance reports. This will include the latency for running the software, then the hit ratios, then the prefetch, then the write backs, then how many of them were evicted. So the write hit ratio, read hit ratio, all of that will be knowing from the Visual Sim architect. So now once we get the results and we see that, okay, this is not so accurate, or the software is not running much efficiently. So for example, like let's say we are running a software code and the hit ratio is around 75%. Now that is not so optimal. So what we would do is we will update the software code, and then we will make some changes in the software code. Then we would again recompile it in target architecture. Then we get the traces again. Then we repeat the process. So this is a looped procedure where we will get a result from the previous stages used to make better result moving forward. So just to give you an overview, what we mean by behavior flow and hardware architecture in Visual Sim, the behavior flow is just a sequence flow representation of how tasks will be executed. And the hardware architecture is a representation of how the hardware architecture of a device is implemented, or the real system, in the real system, how it is implemented. So here we have the behavior flow at the bottom and the hardware architecture at the top level. So we can see here in the behavior flow, when once a trigger comes in, two tasks, task 1 and task 2 are triggered. And for the task 3 to get started, we require the output of task 1 and task 2. So we can say that the task 3 is dependent upon the outputs of task 1 and task 2. So, and the task 1 and task 2 are mapped to, all of these tasks are mapped to this hardware. So we can see here that task 1 and 3, it is mapped to CPU 1. Task 2, it is mapped to CPU 2. So once a task comes into the CPU 2 or CPU 1, once it is getting triggered, the data has to, let's say the I cache or D cache, it has to get the data from the cache which is connected across the buses. If there's a missing cache, it has to go through the bus and to the RAM and then get the data from it. So to just quickly give an example on the Visual Sim on how it means. So here, just a simple example, we have one task and one processor core. So let's say the task latency is 3 seconds. So we can see that for 3 seconds, the task 1 is being executed in the CPU. Now we increase the number of tasks. We can see here that the CPU core or the hardware architecture is still the same. The only change that we have made is add more tasks into the behavioral flow. So this would mean that we are running 3 tasks parallelly. So task 1, task 2, and task 3. So similarly, we can see the task flow diagram from Visual Sim. We can see that task 1 is executed first, then task 2, then task 3. So now, what if there are priorities being added to it? So that would mean that the preemption is being enabled, and we can see how the task plot is changed. So we can see when the task 2 is generated or triggered, immediately the task 1 is preempted and task 2 starts executing. Then when task 3 comes in, which is having a higher priority, task 3 starts executing and then it completes it. And then it goes back to task 2 and then the task 1. So this gives you an idea of how different type of experiments that can be done and how the performance of the system is going to be affected by it. So we can use this. I mean, from the simple example, we can see how adding some overhead task is going to affect the overall performance of the system, how we can map the system task to the hardware architecture, how if the preemption is enabled, how it is going to look different on the performance metrics of it. So also at the same time, this is a table representation of comparison between a real system power profile versus the visual sim power profile. So we could see that for most of the frequencies, we are seeing very close correlation between the real system and the visual sim results. So this table has been formulated by using the data, raw data from anandtech.com, where we have compared it one-on-one with it. So now we are going to look at a few demo models where we can see how the hardware software partitioning can be done, how the power consumption changes between them, and what we can model using the visual sim architect. So this is the block diagram representation of the system that we will be building, and how and the target or the goal of our exploration. So these are our main two goals that we have to achieve. One is the power consumption. It has to be below 2 watts for the entire SoC. And the second target that we have to achieve is the number of frames when 20 milliseconds has to be greater than 50,000. So in order to achieve these two goals, there are mainly 3 different use cases or evaluations that we have done. One is we run all the tasks in the software itself, software device itself. That is just a 53 itself. Then on the second exploration, we mitigated some of the tasks into hardware accelerator just to improve some of the performances. And the third, what we had done is we had added some power management to reduce the power consumption. So this is the device configuration of the systems that we had used for this SoC. So we have the processor core, the Cortex A53 being selected. The processor speed is 1200 megahertz. The L1 cache, the I cache is having a 32 KB size with 2-way set associative. D cache is 32 KB with 4-way set associative. The hardware accelerator is having a speed of 800 megahertz. And the L2 cache is of size 1 megabytes and associated is 16-way. The external DRAM is of size 4 GB. The type is DDR4 and the speed is 2400 megahertz. So this is the corresponding visual sim model that correlates with the block diagram. So we have the hardware architecture defined on top. We have the software architecture or the behavior flow defined at the bottom. So we can see how the software is defined. That is, the sensor gets the data, we read the frame, we decode the frame, then we do video processing, render frame, format conversion, then rotate frame, and then the display task. So in this, while defining the system as an architect, we have different evaluation possibilities. That is, we can maybe, if the architect is looking to do analysis on IP level, then they can evaluate the pipeline stages within the ARM system. The width, the speed of the processor, the speed of the caches, width of the cache system, the data path width, or the number of execution units, the number of cache levels. So it is also possible to add L1 level, L2 level, L3 level if needed to the system itself. Then on the SoC level itself. So in the SoC level, we can add multiple ARM cores. So in this case, we will be, we can add, let's say, some of the tasks. The sensor task is running on core 1, read frame on core 2, decode frame on core 3. Then video post processor on core 1, render frame on core 1, format conversion on core 2, rotate frame on core 3, display task on core 1, and so on and so on. So we should be able to, so this is the overall idea where the architect can map different software tasks to different hardware components. So it can be done according to a fixed setting, or we can use a hypervisor or a scheduler to map the software task according to the availability of the cores as well. So let me take you over to the visual sim model corresponding to it. So this is a visual sim model, and we can see the ARM subsystem. So this is the graphical environment where we model the system that we want to implement. So this is the software flow, and this is the hardware implementation. So I can go inside each of the blocks and see how detailed it is being implemented. So I can see the ARM Cortex A53 being implemented here, the processor block, the pipeline stages defined here, then the processor definitions, instruction queue lines, instructions per cycle, which is 2, then pipeline stages, execution units, floating point units, everything can be defined here in this window. We also have the detailed cyclic rate implementation of the cache unit. So I can double click on the cache and we can see the different parameters associated with it. The cache sizes, then the width of it, then the block sizes, write through or write back, the replacement policies. Then we have stochastic or address based. Then we also have associativity selection over here, the request buffer sizes, fill buffer sizes, then the inclusion policies if needed. All of this can be selected by double clicking on the block directly. Okay, so when I run the simulation by clicking on this play button over here, it will run the scenarios that we have selected here. It will run through the software sequence and generate certain set of statistics. So the statistics that we need will be generated on these pop-up windows. So we can also see that for the entire hardware architecture components, the timing diagram. So we can zoom in and we can see when each of them are happening, the register writes, register read, the integer one execution units. So these are execution units. When are each of them happening? Then the DRAM, the refreshes happening, the bus control signals, bed data signals, then the axis signals. So we can see a whole lot of information by looking at the timing diagram here as well. This is very much useful for debugging. Then we also have the power plots here, and the hardware engine power here, then detailed static summary, which will be available at the end of simulation. So let me take you back to the presentation. So let us look at some of the model parameters available to us. So this is one of the important parameters that we have, that is the select partitioning. So this will let us select whether we want to run all the task in the software, or we have to run some of them specifically in hardware accelerator. So the reason for using the hardware accelerator would be some of the tasks are too resource intensive. So you want to make such tasks run in hardware accelerator so that the process will run a lot faster, but at the expense of power. And we also have a database here where we can we have a column here for the task name. We can see all the different tasks listed here and the destination and the priority associated with it. So the user can, by making some simple changes in the database, like, maybe we can make the read frame priority to be 2, then or 3. According to that, the priority will be different. So as we saw before, when we define the priority accurately, we can see significant improvement in the overall performance of the system as well. So let us do some case study analysis using the this demo model and see how we can achieve the requirements. So let me once again show you the requirements that we are trying to achieve at this one. Basically, there are 2 requirements. One is the power consumption to be less than 2 watts, and the number of frames in 20 milliseconds should be greater than 50,000. Okay. On the first case study, we are just using a single core A53 core, and the analysis that is being done at this point in time, let's assume that there is no software code being written. So if we are not having the software code written, then we need to define how the profile will look like. So we use a task generator module from Visual Sim library to define what would be the profile of the task. So let me just show you quickly how the task generator looks like. So it's a custom task generator where we can define n number of software tasks using this module. So this module uses a file called instruction mix table, that is a text file, where the user can define n number of tasks in different rows. So each row is a task definition, and it each has a task name. So we can see here the sensor task, read frame task, and the task numbers associated with it. So read frame task has only 100 instructions to be executed, decode frame 160, and then we can see that the rotate frame has 1,000 instructions. So we can see the software task column, number of instructions per task, then the number of instructions specific mnemonics. So we can see here that this is a percentage. So this particular, let's take the first row. The IFU type is of having 25%. Branch unit 5.72%. Shift unit 10%. Load store unit 15%. Branch misprediction 0.43%. Then load store unit again 25%. Load unit 25%. Store unit 15%. Then the miscellaneous, the remaining ones 3.85%. Now what does these terms mean? IFU, BU, SU, LU. These are defined at the top part of the instruction mix table itself, where we define the mnemonic or the task descriptor. So for IFU, in floating task, we have defined these instructions to it. So the add instruction, sub instruction, SBCS, CCMN, EON, EOR, these instructions belong to this descriptor. So for BU descriptor, these are the instructions belonging to it. And then for LU, these are the ones, LTU, these are the ones, STU, these are the ones, and so on and so on. So the idea is that when I say LDU to be 25% of the total 276, that would mean that the 25% of the total instructions will be made up of these instructions listed here. So by using this instruction mix table profile, we can define a software profile for each of the tasks. So the reason why we are using this instruction mix table is because at the very earlier stages in the development, we might not be having the software code associated with each of the software tasks. So in that cases, we can use this instruction mix table to define a profile for it. And we can see how the performance of the system is going to look like very early in the software cycle itself. So once I ran that test case, this is the result that I got in. So I can see the power consumption is less than 2 watt, which is what we required. But the performance, that is the number of frames per second, it's less than 50,000. It's a maximum of 23.3 thousand frames. So this is not satisfying all of our requirements. So then we can also see some of the cache statistics as well. So we can see the cache hit ratio, miss ratio, then the number of instructions reaching the caches, number of prefetches happened, buffer occupancy, if any buffer overflow happened, and the latency for each of the caches, the min, maximum, and mean. So this is the round trip time, includes a miss delay as well. Then the read hit ratio, Mbps for read, write, and total. Then write hit ratio, evicted block count, write back block count, and the utilization of each of the cache blocks. So these statistics will be reported by the Visual Sim during the simulation itself. So once I ran this case one, I generated a sequence diagram. And I could see that for each of the trigger, the rotate frame task is taking too much of the resource usage, utilization. So since we found that the rotate task or rotate frame task is one of the most resource intensive tasks, what we did was we ran the rotate frame task on hardware accelerator. So because the rotate frame task is very resource intensive, we partitioned that task to run on hardware accelerator. So after running the simulation, we could see the power consumption is going about 2 watts for the SOC, but this is not one of our, this is not satisfying the requirement. But at the same time, the performance of the system is improved considerably. Now, the performance requirement, the max performance that we can see here is 125,000 frames per 20 milliseconds, which is very much satisfactory. But at the same time, the power consumption is not below 2 watts. So what we, so the observation that has been made is the average power consumption is greater than the threshold that we have defined. So some of the options for the architect at this point in time is to use the hardware accelerator from another vendor. So it could be possible that because we are using a certain hardware accelerator from this specific vendor, the power consumption was much higher. Or the other option is use the same hardware accelerator, but apply power management. So from the, because why we thought about such an approach is that this is the hardware power engine plot, hardware engine power plotted. So we can see the hardware engine is only active for short burst of time, very short period of time. So so then we thought of applying some power management to it. So on the case 3, we ran the frame task on hardware accelerator, but we applied some power management techniques to it as well. So once we applied it, we can see, even though initially it was going above, it was on path to go about through 2 watts, but then due to the power management, it went below. Then we can see over time it becomes saturated and becomes less than 2 watts. At the same time, the performance is not affected at all. So we could conclude that this case 3 was the the best configuration or the required configuration that the user wanted to go with and would satisfy all of the requirements. Now, let us consider another case study environment. This is after we have the software code available for the user. So, and we are using a dual core A53 setup here. Now, since let's assume that the render frame task corresponding software code is ready. So what we did was we executed the software code, the C code and gem file. Then the gem file generated the output traces. Then we use a Python code to parse the gem file output into the visual separatable format. And we use that trace format for generating the instruction sequences and addresses. So let me show you what it means. So we get the software, we execute the software code in gem file. Then we get the output in a text file format. Then we parse the text file using a Python code. And then we generate an output file in CSV format, which will be used as input to the Visual Sim architect. So this is what the C code looks like, a small snippet of it. And we are converting that and after running it on Gem5, we get the following outputs. So we can see the statements like, okay, CPU system T0 running, and it's a move instruction. And this is the just an integer LEO operation. And the address is also, we can see it here. And we can also see here the load store operations. It's a memory read, the address associated with it. We can see all of that as well. Then we use the Python code like this, and then we generate the output file. It's a trace.csv file here. So once the trace.csv is available in the model, we used a traffic reader to read that CSV, and we ran that in loop. The reason why we run it on loop is because we have multiple lines which has been passed. We want to read each line to fully complete the software task execution. So we run this reading in loop, and once the entire traces has been completely read out, we send the output to the next stage. Okay, so also the database was updated with the second code, because in this particular run, we are adding another ARM core to the SoC. So we have two ARM cores, and all the other tasks are running in one core. The render frame is in the new core, which is ARM2. And we could see the following results after simulation, which was pretty good and is very much closer to the runs which we did before as well, and satisfies all the requirements, which is great. So also from the power plot, it is also possible to generate very detailed state plots using. So what I meant by is that this is our power manager, or the module which is responsible for keeping track of all the devices power. And at the bottom, we have an option for state plot enabled. So if I enable it, I can get detailed state plot descriptions for each of the devices. So which is what is shown in this diagram. And we use an open software called GNU-plot for viewing the results from here. So now that we have completed the demo details or the use case study for using an multimedia system, let me show you how we can scale up that design and bring it up to maybe a 16-core demo model using network on chip. So this is a block diagram of the system where we have two A65AE clusters connected to two routers, and we have an L4 cache here and the DRAM connected to the router R112. And this is the components inside an A65AE cluster. So we have 8 cores here within, and each of the core has private cache, L1 I cache, D cache, and the L2, then a bridge which is going to connect to the DSU, which has the L3 cache. So this is the device configuration for the system. The processor core is Cortex A65AE running at 1200 megahertz. iCache is at 32 KB, 4-way set associative. Dcache 64 KB, 4-way set associative. L2 cache 256 KB, 4-way set associative. And L3 cache 512 KB, 16-way associative. And the DRAM is DDR4, 2000 megahertz. So these settings are all configurable for the user as well, because from the real board configurations from the ARM, we could see that the user can increase the sizes, can define different set associativity as well, according to the user requirements. So this is all possible from the system as well. For example, so and this is the visual sim model that is built according to the block diagram. So let me take you over to the model. Sorry, here. So this one, so we can see the behavioral flow or the software flow here, and the hardware description here at the top. I can go inside each of the hardware components here. Then I have the core cluster here, and I can see the processor core here. So we can see how the processor core has been defined, the number of pipeline stages defined here, then the processor description here. So the number of instructions per cycle, the reorder buffer size, then the outstanding request count per caches, everything can be defined using this processor component. And also this is a private caches where we have iCache, Dcache, L2 defined. And for each of the caches, we have the parameter definition described over here. Associativities, stochastic or address-based. We are running an address-based here. Then write back or write through. Then the cache replacement policies between the 3 options that is available here. Okay. Okay. And also one another, this is the instruction set that we have where we define the instruction detail. So for each of the cycle, what is the latency associated with it? All of this can be defined using this file over here, A65AE. So this is a very implemented using cyclic components in a very detailed. And over here, we can see this one. If I double click on the cluster, we can see the parameters listed here. So we have a parameter called mode of operation where the user can define a split mode or a lock mode. So in the lock mode, we will be having processor cores running in a redundant mode where two cores will be running the same software traces and comparing the results against each other. And then the temporal delay cycles, then the redundant coordinates, all of this is provided here. And these are parameters which can be easily modified by the user. So let me take you back to the. So these are the model parameters, and these are the parameters of the router. So we can define the topology for mesh or loop topology, whether we are enabling the priority, then the QoS options, the bandwidth limiter or latency limiter, how do we want to go with it, then the buffer sizes for it, and the bandwidth per port. All of this can be used for configuration as well. So since we are running in lock mode, the same application is run in core as well. That is why we are splitting it up we are using a relation and splitting it up. And same task is running in both the core. And then once it completes, it goes to the next one, then the different task, different task, different task. And once the entire task is over, we plot the latency here. So at the same time, we are running both of the clusters. We are having the software running in both of the clusters. So these are the results obtained from the simulation, and we can see how the MIPS for each of the processor cores are looking like, the core latencies, and so on and so on. And one of the points that we can notice here is that we can see here the MIPS or the MIPS become stable between certain time period. It starts off very low, but then it becomes stable. This is because at the very start, the cache loading is required. So the required addresses needs at the very first 100 instructions or so, there will be a lot of misses. So it has to go through the network and get it from the DRAM and get it back. So there is a lot of loading delay. So the MIPS is considerably low. But once the cache has been loaded, it saturates and we get a significant performance. At the last, we have the write backs happening, and then it considerably lowers down as well as we go along for each of the cores. And for this as well, we get the cache statistics. We can see for each of the cluster, cluster 2, core 7, then core 7 D cache, then we have the L2 cache, then the L4 cache. We get for all the caches in the system, we get the detailed statistics for each of them. We also get the router statistics from the model, where we can see the Mbps per router, R11, R12, R21, and R22. We can see here that R22, the utilization or the throughput is 0 because there's no device connected to the R22 router, which is over here. Let me show you this one. This is R22, and all the no packet goes through here. All of them are taking this path because we are using XY routing algorithm as the routing. And this is the same model when we are running the split mode. So since it is split mode, there is no need for running it in redundant mode. So we can see how the software is mapped. So according to the way or the application type, so if it is an automotive application or if it is a fault tolerant application, then we will have to run it in lock mode. Otherwise, we can run it in split mode and use all the available cores running different software tasks. So we are running different applications, are running different application running on each of the cores in this particular run. So, and one of the last demo models that we would like to discuss is the software mapping in a network processor. So here we can see we have a network on chip system here, and then we have multiple processors. Processor 1, processor 2, we have a security processor here, we have a DMA here, we have an external CPU here. And this is the hardware system, and this is the software mapping that is defined at the bottom. So if I take you to the model, we can see this is a sequence of which happening. So we can see here, the packet comes into the network via 5MAC here. Then DMA is triggered for transferring the data to the main memory. Once the data is transferred, security tasks are executed. We can see here, once the interface task is over, the security task is getting triggered. Now, once the security task gets over, the header processing, the control plane operation will take place. So because the header processing is intensive, we make use of external CPU along with the processor cores for this purpose. So once this is going to external CPU, this is going to the processor one, and once both of them gets completed, we are we are mapping the process that the forwarding process is done on the processor two, the data plane processing. And once all the tasks are over, we are transferring it back to send the data back to the MAC. We read it from the memory, and then the DMA will read from the memory and send it back to the MAC, and we get the data here. So once the entire sequence is completed, we calculate the latency and we plot it. So these are the results that we can observe from the simulation on before. So we can see here the network latency for each of the masters are plotted here. So we can see even though it is a specific sequence, according to the traffic arrival in the 5MAC interface, there at a certain point in time, all the processes are active. The network usage is very high, and the latencies we can see at certain times, it is having a certain burst in latencies. So certain spikes we can observe over time here. And then the buffer occupancies per each of the device ports, we can see the power plots we can observe as well. The spikes in between sequences can be observed as well. So with this, I would like to conclude by reiterating how the architecture exploration can be made easy, fast, and accurate by using the system modeling tool such as Visual Sim Architect. The reason why this is worthwhile to invest in is because the results that has been generated from Visual Sim Architect has been validated while comparing it with the real system. So with this, the user also has the ability to model different parts of the system. It can be a certain IP core, it can be a particular part of the system, network system, or the entire SoC itself. We can integrate components from different vendors into the same system without worrying much about the protocol conversion requirements. So with this, I would like to wrap up today's webinar discussion on the topic energy efficient AI workload partitioning on multi-core systems. Now we feel free to ask any queries or doubts you have on the system. And one other thing I would like to mention here is that I will be sending you the recording of this session along with the PowerPoint presentation. There are a few other material that hasn't been discussed, which are added at the end of the material, that is in the backup slides, where you can see the ultra scale demo, some of the analysis that has been done, all of it can be observed from here as well.